Next problem. So C1, so it says here, right, calculate the wavelength and frequency of the sulfur KH signal, right? So if we're looking at the spectrum that was collected by the Spirit rover, that's, an APS X-ray spectrometer, what we can see right here, right, is that the sulfur K edge is located right here. So that comes out to being about, what is it, like 2.1 kilo electron volts. So the energy that we're looking at in this case is 2.1 kilo electron volts, which is equal to, 2.1 times 10 to the third electron volts. And so what we can easily do for ourselves, right, is we can use that equation that we had used in the past to calculate everything, right? And so or we can just simply just use these right here, right? So this is equal to h nu. So h, right, is Planck's constant, nu is the frequency in this case. And so if we want frequency, the frequency is then going to be equal to Planck's constant, right? So that's simply going to be h over e. So that will be equal to 6.626 times 10 to the negative 34 joule seconds over, one thing we have to do, right, we have to convert it into joules, and so that's fine, right? We have, 2.1 times 10 to the third electron volts, and so we know to do that, right, is that 1 electron volt is equal to 1.60218 times 10 to the negative 19 joules, right? Joules cancel, electron volts cancel. Wait, no, this is wrong. Just gonna edit this because nobody's watching right now. Right, so we have let me just take this whole thing because it's just me, I think, on the stream. And so when I cut this up for the highlight later, I can just go from the scratch. But yeah, okay. So right, so what we're doing here for C1 is we're calculating the wavelength and frequency of the sulfur K edge, right? So we can see the sulfur K edge is right here within the spectrum, right? So everything has already been identified in this case, right? Sulfur has the elemental symbol S, and so that comes out to being about 2.1 kilovolts or kilo electron volts, right? So the energy is equal to 2.1 kilo electron volts, so that's the same as 2.1 times 10 to the third electron volts, which is then going to be equal to h times nu, right? H times the frequency in this case. So if we're trying to get the frequency, right, the frequency is going to be equal to the energy over Planck's constant. So what we can do is we can plug in our numbers, right? So we have 2.1 times 10 to the third electron volts over 6.626 times 10 to the negative 34 joules per seconds. And so then the one thing we have to do too, right, is we have to cancel out the joules and the electron volts so we can get to 1 over second. So to do that, right, all we have to do is multiply 1.60218 times 10 to the negative 19 joules over 1 electron volt, right? So that means electron volts cancel, joules cancel, and we end up with 1 over seconds. And so the frequency is 2.1 times 10 to the third divided times 1.60218 times 10 to the negative 19 divided by 6.626 10 to the negative 34. And so that comes out to being 5.08 times 10 to the 17 per second, or hertz, right? And so I got 5.32, here's 5.08, right? Like, it's close enough, I think, in terms of where I may have decided. I may have decided, right, that it was like maybe 2.15 kilo electron volts within the key, but that's pretty close. And And so then, right, for wavelength, right, is just simply equal to C over nu, right? So 2.9979 times 10 to the 8th meters per second divided by 5.08 times 10 to the 7th, 1 over seconds, right? Seconds cancel, so you end up with meters. So what we get is 2.9979 times 10 to the 8th divided by 5.08 times 10 to the 7th. 17th, not 7th. I was about to say, I was like, my units are very off here. So that comes out to 5.90 times 10 to the negative 10 meters. Right, which is pretty close to what I have right in the answer key, right? That's 5.6 times 10 to the negative 10 meters. So again, it kind of just depends on like where you put down the what the energy is of that K edge in these cases. Without doing any calculations, do the X-rays emitted from the excitation of aluminum have a longer or shorter wavelength than the X-rays emitted by sulfur, right? So we know where sulfur is, and so now looking at aluminum, right, we can see aluminum is right here. So aluminum comes in at around 2.4 or so kilo electron volts. So it has less energy, right? It's at a lower energy. So if it's at a lower energy, then that means that it's going to be at a longer wavelength, right? So remember that there's that inverse relationship between, wavelength and energy in those cases, right? So frequency scales with, with energy, whereas wavelength has an inverse relationship in that case. So in this case right here, right, the wavelength would be longer for aluminum. How does the position of the elements on the periodic tables correspond to the energies of the X-rays released, right? So if we're looking at it, we can see, right, we have sodium, magnesium, aluminum, silicon, sulfur, chloride, phosphorus, right? Well, phosphorus is before the sulfur, right? So just simply looking at it, right, it matches with the elements on the periodic table, right? So as you move across a row, right, the energies of all of the different K edge excitations all relate to their position on the periodic table. So as essentially Z, right, the atomic number increases, the values of the in the APXS spectrum increases as well, right? You can see the same thing happening down here where you have titanium, chromium, manganese, iron, right? All of those are just simply going in a series in these cases, right? And they're all increasing as they go. So increases with atomic number.